Today in this video, we want to discuss and compare the values of displacement and velocity and acceleration of a body in simple harmonic motion. To do that, first we shall remember back what are the equations that we have derived in the previous videos for them. We have proved that displacement y is equal to a sine omega t. We have derived this expression. We have also derived expressions for velocities, accelerations, and say for example, velocity expression is derived as something like omega of root of a square minus y square, or in the other sense, we have proved it as v equal to a omega cos omega t. We have also derived an expression for acceleration as minus omega square a sine omega. So if you notice little carefully, each of them varies with time. So under different time intervals, what is the values of this displacement, velocity, and acceleration, and where are they located as? That's what we want to discuss in this video. Yeah. So what's the intervals that we would like to count is, say for example, at time is equal to 0. So let's write each of these equations at time equal to 0. For example, displacement is y equal to a sine omega means 2 pi by t, and time. At what time we want to calculate? Time equal to 0. So displacement is 0. What is velocity is? This is our expression. Yeah. A omega cos omega. Again t equal to 0. So when t is equal to 0, it becomes something like this is sine 0 actually. Sine 0 is 0. But this is cos 0. Cos 0 is 1. So its value becomes a omega, which is the maximum possible value. Again, the equation for expression is, for acceleration is minus omega square a sine omega into t is 0. Again, sine 0 is 0. So this value is 0. So if you notice, the values, displacement is 0, velocity is maximum, acceleration is 0. Now look at this graph. Here in this graph, we are taking time in each of the graph onto the x-axis, and this graph on y-axis we have displacement. For this graph on y-axis we have velocity. For this graph on y-axis we have acceleration. So if you notice, at time equal to 0, that is at the origin, as displacement is 0, we have started our point here. And velocity is maximum. That's why if you notice, graph has not started from origin, but rather started from maximum. That is a omega. Again, acceleration is 0. It has started from origin. These are our respective values for t equal to 0. Now let us write at another case, at another location, at t equal to 1 by 4th of the time period. Let us substitute this t equal to t by 4 in all these three equations once again. Yeah, tell me what happens for the displacement. A sine omega t. Omega is 2 pi by t, and we want at a time of the place of t, t by 4. So this and this will cancel, this and this will cancel. It becomes sine pi by 2. That is sine 90. Sine 90 means that is equal to 1. So a into 1, that is a. And if you notice, that's the maximum possible displacement. That's why at t by 4, if you look at here, the graph is at maximum. Displacement graph is at maximum. That is a. Let's talk about velocity. A omega cos 2 pi by t is omega, and in the place of t, t by 4. So t and t will cancel. This will cancel. This becomes pi by 2. That is cos 90. We know sin 90 is 1, but cos 90 is 0. So the respective velocity is 0. So look at the graph. At t by 4, velocity becomes reach at the say x-axis of that. Let's have a look at the acceleration. Minus omega square a sin omega t, 2 pi by t and t by 4. So this becomes again pi by 2. Sin 90, pi by 2 is 1. So this value is minus omega square a. Be careful, it is negative. That's why at t by 4, graph is negative maximum, minus omega square a. Graph has reached the bottom of that. So if you join these points from say t equal to 0 points to these points, this set with this set, you can get a kind of a graph. See this, how the graph is progressing. Yeah. Which graph is progressing slightly different. And if you notice little carefully, you will get the same even if you do further. If you notice little carefully, when, see, look at this t equal to 0 case. When displacement is 0, yeah, I'll take another color. When displacement is 0, velocity is maximum. So they are in having a phase difference of 90. We will talk about the phase difference a little later in a further video. But they are opposite to each other. One is 0, another one is maximum. And then again, let's see. This is equal to 0. So you can notice one is 0, one is maximum, another one is 0. Look at here. At t equal to t by 4. This is maximum, this is 0, and this is negative maximum. So from here to here, there is a difference of 90-degree phase. Here to here also there is a difference of 90-degree phase. We'll talk about that phase later in a further videos, but I just want you to notice that each one, say for example, what's the point that I would like to tell you is velocity amplitude differs by 90 degree. Again, velocity acceleration differs by 90 degree. Displacement acceleration, the first one and the last. So from here to here, there is a 90-degree phase difference. From here to here, there is a 90-degree phase difference. Then from first to last, the phase difference is 90 plus 90. That is 180-degree phase difference. So velocity, sorry, displacement and acceleration are opposite to each other. That's why we call that motion as a simple harmonic motion. That's what the basic intention of saying that. If you proceed further and find the values for say at t is equal to t by 2 and then at 3t by 4 and at t, you can get a continuation of this graph. You can see how does the graph, each of this graph proceeds further. I just want you to do that yourself and check. But I just want to tell you that from this graph, we can conclude that displacement and acceleration are opposite to each other, having a phase difference of 180 degree. That kind of, they're of course proportional, but they're opposite to each other. That kind of a motion is called as a simple harmonic motion. That's the intention of this part, right? Please proceed and find out for these two values also. And let me just comment in the video if there is an issue. Thank you for watching.